Welcome to chapter 5.5 in our calculus text, which is linearization. And what we are going to be talking about in this chapter is the idea of local linearity. So let's dive straight into an example that will demonstrate what's interesting about this. And I'm going to start with this fairly complicated looking function. And if I graph this, what I get is there appears to be a cusp or a corner right here at x equals 0. And that cusp or corner is at x equals 1. So one thing you could do would be to put that into your calculator and just zoom in, zoom in, zoom in, zoom in. And you zoom in a lot and it keeps looking like there's a cusp or a corner there. But let's take the derivative. The derivative of this function is 1/4 x squared plus 0.0001 to the negative 3/4 times 2x. And doing a little simplifying, we get that this is x over 2 x squared plus 0.0001 to the 3/4. And what we notice is that the denominator is greater than 0 for all values of x. So this part right here is greater than 0 for all x, which means that the slope of this function at x equals 0 is 0. In other words, this graph has a horizontal tangent at x equals 0. It is not a corner. It is not a cusp. In fact, if you zoom in far enough, what you discover is that you get a graph that looks like this, right at x equals 0, y equals 1. Which means that if we get close enough for numbers close to 0, we can just say, oh, y is equal to 1. So what are the ramifications of this? Well, definition, if a function is differentiable at a, then the tangent line L of x is equal to f prime of a times x minus a plus f of a is the definition of linearization. Definition of linearization at x equals a. Now, you'll notice that we are calling this L of x just to show that it's linearization, not just a tangent line, but a special tangent line, which is that we're going to approximate this function as the tangent line for values of x very close to the actual, or to a. So we can go a little bit on either side of a, and we're going to assume that these two functions are approximately equal in that range. So what we say is that for the purposes of linearization, f of x is approximately equal to L of x, and this is called a standard linear approximation. Excuse my voice, I've got a bit of a scratch today. This is called a standard linear approximation, and we can say that the function is approximately equal to the linearization. Um, so I'm going to stop there because I have another video, actually the next 1, 2, 3 videos. So videos 2, 3, and 4 are all going to cover examples of linearization. They're all fairly short videos. And so I'll leave you with that definition and let you dive into the next videos to look at examples of how we use this. All right. Thanks for watching.